Hey there, physics enthusiasts. Welcome back to our channel. Today, we're embarking on an epic journey through the fascinating world of physics. Buckle up, because we're about to explore everything from the tiniest particles to the vast expanses of the cosmos. Before we dive in, take a moment to look around you. Everything you see, touch, even the air you're breathing. It's all governed by the laws of physics. Mind-blowing, right? Physics isn't just some abstract concept in a textbook, it's the very fabric of our reality. So let's start unraveling this fabric together. Let's kick things off with classical mechanics. This is the foundation of physics, describing how objects move and interact. Picture this. You're at a party, and there's a delicious pizza just sitting on the table. It's not going anywhere, right? That's Newton's first law in action. Objects at rest stay at rest unless something acts on them. In this case, that something is hopefully you grabbing a slice. But what if you're sliding across a slippery floor at that same party? You'll keep moving until you hit something or someone stops you. That's the flip side of Newton's first law. Objects in motion stay in motion unless acted upon by an outside force. Now, I know what you're thinking. But things don't keep moving forever in real life. And you're right, that's because in the real world, there are always forces acting on objects, things like friction and air resistance. These forces slow things down over time. But if you could somehow remove all these forces, yep, you'd keep sliding forever. Okay, so that's what happens when there's no force, or when forces are balanced. But what about when you do apply a force? This is where Newton's second law comes in. It tells us that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. In simpler terms, the more force you apply, the faster something accelerates. But here's the catch. The more massive something is, the more force you need to get it moving. Ever tried to push a car? Yeah, it's not easy. That's because cars have a lot of mass, so you need to apply a lot of force to get them moving. Let's break this down with an example. Imagine you're pushing a shopping cart. If you push harder, more force, the cart will accelerate faster. But if you fill that cart up with groceries, increasing its mass, you'll need to push harder to get the same acceleration. This relationship is often written as F in Chasson May, where F is force, M is mass, and A is acceleration. And here's a fun one. Newton's third law. For every action, there's an equal and opposite reaction. It's like a cosmic game of ping pong. When you jump on a trampoline, you push down on it, and it pushes right back up at you with the same force. Cool, right? This law explains all sorts of things. When you're swimming, you push water backwards, and the water pushes you forward. When a rocket launches, it pushes exhaust gases downward, and those gases push the rocket upward. Even when you're just standing still, you're pushing down on the earth with your weight, and the earth is pushing back up on you with an equal force. Now let's talk about some important concepts in mechanics. Momentum and energy. Momentum is basically the oomph of a moving object. It's the product of an object's mass and its velocity. The cool thing about momentum is that it's conserved in closed systems. This means that in a collision, the total momentum before and after the collision is the same. Think about a game of pool. When the cue ball hits another ball, it transfers some of its momentum to that ball. The cue ball slows down or stops, while the other ball starts moving. The total momentum of the two balls together stays the same before and after the collision. Alright, let's shift gears and talk about energy. Energy comes in many forms, but in mechanics, we often focus on two types: kinetic energy, the energy of motion, and potential energy, stored energy due to position or configuration. You know that feeling when you're at the top of a roller coaster, just about to drop. That's potential energy, baby. As you plummet down, that potential energy turns into kinetic energy, the energy of motion. It's like the roller coaster is doing an energy dance, constantly converting between potential and kinetic. This conversion between potential and kinetic energy happens all around us. When you lift a book, you're giving it potential energy. When you drop it, that potential energy converts to kinetic energy as it falls. When it hits the ground, some of that energy converts to sound energy, the thud you hear, and some to heat energy. The book and floor warm up slightly on impact. One of the most fundamental principles in physics is the conservation of energy. Energy can't be created or destroyed, only converted from one form to another. This principle underlies everything from the way your body metabolizes food to the way stars shine. Speaking of roller coasters, let's chat about work and power. When that coaster car is being pulled up the first big hill, the motor is doing work, applying a force over a distance. The rate at which it does this work, that's power. So a more powerful motor could yank you up that hill faster. In physics terms, work is done when a force causes an object to move in the direction of the force. If you push against a wall but it doesn't move, you're exerting a force, but you're not doing any work. In the physics sense, at least, your muscles might disagree. Power is the rate at which work is done, or energy is transferred. It's why we measure car engines in horsepower and light bulbs in watts. A more powerful engine can do the same amount of work in less time, or more work in the same amount of time. Now let's talk about something that keeps us all grounded. Literally. Gravity. It's the force that keeps planets orbiting stars, moons orbiting planets, and you firmly planted on Earth's surface. Newton's law of universal gravitation tells us that every particle in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. In simpler terms, everything attracts everything else, but the attraction is stronger for more massive objects and weaker for objects that are farther apart. This law explains why planets orbit the sun, why the moon causes tides on Earth, and why you don't float off into space. It's a fundamental force that shapes the large-scale structure of the universe. But gravity isn't just about keeping things down. It's also responsible for some pretty cool phenomena. Like tides, the moon's gravitational pull causes the oceans to bulge out on the side facing the moon, and the side facing away from the moon, creating high tides in those areas. Gravity also plays a crucial role in the life cycles of stars. It's the force that causes gas and dust to collapse into new stars, and it's the force that a star must constantly fight against to avoid collapsing in on itself. When a star runs out of fuel, gravity wins this battle, leading to some of the most spectacular events in the universe, like supernovas and black holes. All right, now let's heat things up a bit and talk about thermodynamics. Thermodynamics is all about heat, temperature, and their relation to energy and work. It's governed by 4 fundamental laws that describe how thermal energy is converted to and from other forms of energy and how it affects matter. The zeroth law of thermodynamics is like introducing 2 friends to each other. If System A is in thermal equilibrium with System C, and System B is also in thermal equilibrium with System C, then A and B must be in thermal equilibrium with each other. It's like saying, if you and I are both comfortable at 70 TRF, then we're comfortable with each other's temperature. The first law of thermodynamics is essentially the law of conservation of energy applied to heat and thermodynamic processes. It states that the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. In other words, energy can't be created or destroyed, only converted from one form to another. This law explains why your car engine gets hot as it runs. The chemical energy in the fuel is being converted to mechanical energy to move the car, but some of it is inevitably converted to heat energy in the process. The second law of thermodynamics introduces the concept of entropy, a measure of the disorder in a system. It states that the entropy of an isolated system always increases over time. This is why your room naturally gets messy over time, but never spontaneously cleans itself up. This law has some profound implications. It's why heat always flows from hot objects to cold objects, never the other way around. It's why you can't build a perfect heat engine that converts all its fuel energy into useful work. And on a cosmic scale, it suggests that the universe is heading towards a state of maximum entropy, sometimes called the heat death of the universe. The third law of thermodynamics states that as a system approaches absolute zero temperature, all processes cease, and the entropy of the system approaches a minimum value. It's like trying to get to the bottom of a bottomless pit. You can get really close, but you'll never quite reach it. These laws of thermodynamics underpin everything, from how your refrigerator works to how stars generate energy. They're fundamental to our understanding of energy and its transformations. Now, let's make some waves. Waves are disturbances that propagate through a medium, transferring energy without transferring matter. Think about when you drop a pebble in a pond. The water waves move outward, but the water molecules themselves just move up and down. Waves have some interesting properties. Their amplitude is the maximum displacement from equilibrium. Think of it as the height of a water wave. The wavelength is the distance between two consecutive crests or troughs. The frequency is how many waves pass a fixed point in a given time. And the speed is how fast the wave travels through the medium. These properties are related by the wave equation, VRFL, where V is the wave speed, F is the frequency, and L, lambda, is the wavelength. This equation tells us that for a given type of wave in a particular medium, the product of frequency and wavelength is constant. Waves can do some cool things. When two waves meet, they can interfere with each other. If the crests of one wave align with the crests of another, they reinforce each other, creating a bigger wave. This is called constructive interference. If a crest aligns with a trough, they cancel each other out. That's destructive interference. You can see interference patterns in everyday life. Ever notice those shimmering patterns when sunlight reflects off a soap bubble or an oil slick on water? That's interference at work. Waves can also bend around obstacles or spread out after passing through an opening. This is called diffraction. You can hear diffraction in action when you hear sound coming from around a corner. And when waves hit a boundary between two different media, they can reflect, bounce back, or refract, change direction. Understanding waves is crucial for many areas of physics and technology. Sound waves, light waves, radio waves, even the quantum mechanical wave functions of particles. They all obey these basic principles of wave behavior. Speaking of waves, let's shed some light on optics, the study of light and its interactions with matter. Light is a special kind of wave, an electromagnetic wave that can travel through empty space. It exhibits all the wave phenomena we just talked about, plus some unique properties of its own. For instance, light can be polarized. Its waves can be made to oscillate in a single plane. This is how polarized sunglasses work. They only let through light waves oscillating in a specific direction, reducing glare. Light also behaves differently when it passes through different materials. This is why a straw in a glass of water looks bent. The light is being refracted as it passes from the water to the air. This principle is used in lenses to focus light, allowing us to create technologies like eyeglasses, cameras, and telescopes. The behavior of light as it passes through different materials is described by Snell's law, which relates the angles of incidence and refraction to the refractive indices of the materials. This law is what allows us to design optical instruments with precision. But light isn't just a wave, it's also a particle. This mind-bending concept is called wave-particle duality, and it's a key principle of quantum mechanics. Light particles are called photons, and they carry discrete amounts of energy. This dual nature of light was a major puzzle in physics in the early 20th century. Some experiments, like the photoelectric effect, which Einstein explained, earning him the Nobel Prize, could only be explained if light behaved like particles. Other experiments, like Young's double-slit experiment, could only be explained if light behaved like waves. The resolution? Light is both a wave and a particle, depending on how you look at it. This strange duality isn't just true for light, it's a fundamental property of all matter and energy at the quantum scale. Now let's charge things up and talk about electricity and magnetism. These two phenomena are intimately related. Moving electric charges create magnetic fields, and changing magnetic fields induce electric currents. This relationship is the basis for many technologies we use every day, from electric motors to generators to transformers. Electric charge is a fundamental property of matter. Like charges repel each other, while opposite charges attract. The force between two charges is described by Coulomb's law. It's proportional to the product of the charges and inversely proportional to the square of the distance between them. Electric current is the flow of electric charge through a conductor. In most materials, this current is carried by electrons. The flow of current is governed by Ohm's law, which states that the current through a conductor is proportional to the voltage across it and inversely proportional to its resistance. Ohm's law is usually written as V/IR, where V is voltage, I is current, and R is resistance. This simple relationship is the basis for analyzing electric circuits, from the simplest battery and bulb setup to complex electronic devices. Magnetism arises from the motion of electric charges. Every electron acts like a tiny magnet because of its spin. In most materials, these magnetic fields cancel out. But in ferromagnetic materials like iron, they align to create a strong magnetic field. The relationship between electricity and magnetism was unified by James Clerk Maxwell in the 19th century. His famous equations describe how electric and magnetic fields are generated and interact with each other and with charges and currents. These equations also predict the existence of electromagnetic waves, including light. Maxwell's equations are to electromagnetism what Newton's laws are to mechanics. They're the fundamental rules that govern the behavior of electric and magnetic fields. They explain everything from why magnets stick to your fridge to how radio waves propagate through space. The unification of electricity and magnetism into a single theory of electromagnetism was a major achievement in physics. It showed that what were once thought to be separate phenomena were actually two aspects of the same fundamental force. This unification had profound implications. It led to the development of technologies like radio, television, and wireless communication. It also paved the way for Einstein's special theory of relativity, which was born from considering the implications of Maxwell's equations. Now, let's take a quantum leap into the weird and wonderful world of modern physics. At the beginning of the 20th century, physicists discovered that the laws governing the microscopic world of atoms and subatomic particles are very different from the classical laws we've been discussing. One of the first revolutionary ideas was Einstein's special theory of relativity. It's based on two simple postulates. The laws of physics are the same in all inertial reference frames, and the speed of light in vacuum is constant for all observers, regardless of their relative motion. These seemingly innocuous statements lead to some mind-bending consequences. Time dilation means that moving clocks run slower than stationary ones. Length contraction means that objects appear shorter in the direction of motion. And perhaps most famously, mass and energy are equivalent, related by the equation E = mc2. This equation, E mc2, is probably the most famous equation in all of physics. It tells us that mass and energy are interchangeable. A small amount of mass can be converted into an enormous amount of energy. This principle is what powers nuclear reactors and nuclear weapons, and it's also what powers the stars. But Einstein wasn't done yet. His general theory of relativity describes gravity not as a force, but as a consequence of the curvature of space-time caused by the presence of matter and energy. This theory predicts phenomena like the bending of light by massive objects, the slowing of time in strong gravitational fields, and the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. General relativity has been confirmed by numerous observations and experiments. It explains the precession of Mercury's orbit, which Newtonian gravity couldn't fully account for. It predicts the gravitational lensing of light by massive objects, which has been observed many times. And it predicts the existence of gravitational waves, ripples in space-time caused by accelerating masses, which were first directly detected in 2015, a century after Einstein first proposed their existence. While Einstein was revolutionizing our understanding of space, time, and gravity, other physicists were uncovering the strange behavior of matter at the atomic and subatomic scales. This led to the development of quantum mechanics, a theory that describes the behavior of matter and energy at the smallest scales. Quantum mechanics introduces some truly bizarre concepts,